So here's problem 15. It says that the time rate of change of population is some parameter A times the population, and this is the population right now. So P is not a constant, it's a function, minus a different parameter B, lowercase b here, and then P squared. And we're going to call the birth rate AP and the death rate BP squared. This is an algebraic variant of something that we already know, because we looked before the big freeze at the logistic model, which is a goal-seeking population model. We know that the first population models we got were exponential, and in a narrow time time band, they may work pretty well to model a population, but not in the long run, because they have either collapsed to zero, necessarily collapsed to zero, or infinite growth. And a real population, if it collapses to zero, that can happen, but then there's nothing to study. And an infinite growth is not possible because you run out of resources. So the logistic model was developed to somehow ameliorate those extremes by setting in a carrying capacity as part of the model. And this is in problem 15, we're actually giving you a model that turns out to be a logistics model. And you can see that this way. I'm just going to use algebra on the problem 15 so that P prime, and we're going to factor out of the equation we started with, a B times P. That would be this B right here, the B times P. And if we do that, then the form is BP times the quantity AB minus P. And then if we just introduce some new unfamiliar symbols for these constants, which are parameters, if we would let B be a lowercase k and A over B be an uppercase M, then the equation looks like what I've got here in the middle of the first paragraph. B prime, P, let me say it again, P prime is equal to KP times the quantity M minus P. And that we recognize as the classical logistic equation, where K depends upon the rate of change of the population, births and deaths, and M is the carrying capacity. So the limit as time goes to infinity will be M. So this looks different, and it identifies AP and BP squared as something new, but it's really not something new to us. Problem 17, same page, says to use problem 15 to model this situation. Let me get my textbook. Consider a rabbit population, P, satisfying the logistic equation of problem 15. If the initial population is 240 rabbits, and if there are 9 births per month and 12 deaths per month, initially, that is at time t equals 0, then how many months does it take for P of t, the population, to reach 105% of the limiting population? Now, we've looked at some graphs, and we know the behavior of this logistic equation is that, quick sketch, is that if this is a time axis, and if M, this would be a population axis, if M is about here, then let me just dash in Y equal or P equal M. If we start with a P0 that's above M, the equation says the population will decrease and asymptotically approach P equal M. But if, on the other hand, if we start with a population that's less than the carrying capacity, then the population will grow until it asymptotically approaches the carrying capacity. So it's sort of a self-correcting population model. M would be the carrying capacity or the equilibrium solution. It's the long-term solution to the differential equation, P equal M. And you've got two ways to get there. All right. So this 240, it will turn out, is going to be more than the carrying capacity. So we start out with 240 rabbits. That's possible. You get an island and you dump 240 rabbits on it, but that's too many rabbits for the island. So it says, the logistic model says that this is what will happen to the population, that will slowly decrease until the number of rabbits matches the carrying capacity of the island, and then you're in stasis here, or in equilibrium. The initial births given in this problem, 9 per month, and the initial deaths, 12 per month. When will the population be 105% of the capacity? So 105% of the capacity would be, up here somewhere. So the question is, at what time, where out here, does the population equal 105% of the capacity? So that's the problem. Now, what do we know? We know that from problem 15, A, P0 would be equal to A times, and P0 is given in this problem as 240, so A times 240. And that would imply that A would be I've always said, thank God I've got an eraser. I forgot to write the 240 from the problem. The initial births per month is 9. So A times 240 is equal to 9. From problem 15, the initial birth rate is AP. So A times 240 is equal to 9. And A is equal to, when you reduce it, 3 over 80. We also know that B, P0 squared, is equal to B times 240 squared. And that would be equal to, given in the problem, the initial deaths per month is 12. So that would be equal to 12. And from that, we can see that B is equal to, well, it will turn out to be 1 over 4,800. Of course, it'd be 12 over 240 squared, which reduces to 1 over 4,800. So then with this computation, our differential equation becomes P prime, time rate of change of population, is 3 over 80 P minus 1 over 4,800 P squared, not P2, P squared. See how this eraser comes in handy? P squared. And then with just some algebraic manipulation, because why would I do this algebraic manipulation? Well, I can look at this differential equation and see that here's dp dt, but on the right-hand side, all I've got is p's. And so it's going to be a variable separable differential equation. So I might as well get this into a form where it's going to be easy to put it on left-hand side. And what I'll want to do would be to divide through by whatever this is, because I don't want a big sum and difference over here. I want something times p prime. So let's do the algebra, and this will be 4,800, 180 p minus p squared. And now it's super easy to see that this is variable separable. Differential equation, and of course, first order. So classifying these rascals is still important. Well, then we can write 4,800. Let's leave the 4,800 where it is. Let's write 1 over 180 p minus p squared dp is equal to 1 over 4,800 dt. There would have been nothing wrong with taking the 4,800 and putting it over on the left-hand side. I chose to do it this way. Now all we have to do, since it's variable separable and we've now separated the variables, is to integrate. So let's form teams here. I'll do the right-hand integral and y'all do the left-hand integral. I'm just kind of messing with you because this one is elementary, right? It's going to be t plus a constant. Do you see what this one's going to be? Or do you recognize the technique? I'm not looking for an answer right now. I'm just looking for a technique. How are we going to integrate that?
Use substitution? Oh, no, never mind.
Well, I mean, that's an okay guess, because for integrals that look like this, there are 3 techniques that you've learned that often work, and substitution is the first. And the second is integration by parts. So this is all calculus 2. And you work a lot of problems in calculus 2 that you can solve by substitution or integration by parts. This doesn't happen to be one that works with either of those. What's the third technique that you learn in calculus 2? And we don't hit that one as hard as we do the first 2. What's the missing technique? Erica?
I'm thinking, but I can't remember.
Okay, that's okay. That is okay. Partial fractions. Do you remember partial fractions? So if the denominator here is a polynomial, then the technique is we reduce this, we factor this to irreducible factors. And then for linear factors, we get a term with a constant numerator. And for quadratic factors, we get a term with a linear numerator. More specifically, what I'd want to do would be to take 1 over 180 p minus p squared. And I want to write that. Now I'm going to have to factor this denominator, but the factoring is not hard. In this case, 180 p, and then 1 minus p would be what would be left, right? Or not 1 minus p, but there's nothing wrong with writing that. Wasn't what I wanted. P, and then this would be 180 minus p. So this is how we would factor this quadratic. And this time it factored into linear factors. Now I want to add those, and then this would have a numerator a, and this would have a numerator b. And what I'd want to do next, kind of put the calculus aside, is to find the values of a and b. Because if I can find A and B, then this integral will be the sum of these two integrals, dp, dp, dp. These will be constants, A and B. So this is just going to be a log function. And this is going to be some kind of a log function also, isn't it? I'd probably put a minus here and make this p minus 180. And then I'd use substitution and see that it's a log function. So there's a technique for finding these coefficients, A and B, or if, so this is just review, if you have quadratic factors in the denominator, then you'll get a numerator that looks like cx plus d. And so here you'd have to find, let's call this x minus some k squared, a quadratic factor. Then the numerator would be a cx plus d, and you'd have to find c and d. And I'm going to give you a day or two to get out your calculus 2 and to review the work with partial fractions. I'll probably even give you a partial fraction problem to solve on a very practical matter, practical technique. These can be difficult sometimes. Wolfram Alpha will solve partial fractions for you. And so you give Wolfram Alpha the command partial fraction, and then you would give it this form, and it will tell you what the A and B is and what the denominators are. So I think it's worthwhile to review the material on partial fractions from Calculus 2, because it is one of 3 major techniques that you learn in Calculus 2. But if you have a really tough problem and get stuck on a partial fraction, don't forget Wolfram Alpha, and other computer algebra systems are there to help. It will turn out in this case that 1 over 180p minus p squared is equal to 1 over 180. No, this is just a p. One over p plus 1 over 180 minus p. And so then the integral becomes easy enough, and we wind up with a natural log p over p minus 180 is equal to 3 over 80 t plus an arbitrary constant. And we're almost done. I'm only turning the page because I don't want to make a mistake here. And therefore, and what follows is not differential equations, it's just algebra. P is equal to 180 over 1 minus c e to the negative 3 over 80 t. But we have an initial condition. The initial condition is that p of 0 is equal to 240. So we can use the initial condition. That makes this an initial value problem. And the initial condition will tell us what the value of c is that will change this from a general solution, which is what we have right here, to a particular solution, one that matches this particular plot of ground and set of rabbits. And so whenever I use p of 0 equals 240, we're going to find that c is equal to 1/4 or 0.25. So using that value, we get P of t is equal to 180 over 1 minus, and I could use a decimal or the fraction, e to the negative 3 over 80 t. And then the question is, this is a particular solution. And the question is, when is P of t equal to 1.05 m? Now, before we can answer that, we have to identify m, but this is a logistic equation. And from the form of the equation, we know that when we put the solution into the form that I have it in right here, the numerator is m. So we'll make a note, m is equal to 180, 1.05 times m is equal to, who would know that? Well, you get out your calculator, 189. So for what t is 189 equal to 180 over 1 minus 1/4 e to the negative 3 over 80 t, and it turns out t equals 44.22 months. And of course, you get that by just solving this equation for t. And so you're going to get e to the negative 3 over 80 t is equal to something, and then you'd take logarithms to get the t out of the exponent. And again, that's just algebra, but t is equal to 44.22 months. I like that little problem there, and I included it because it reminds us that the calculus is the background for the differential equations, and partial fractions is a neglected part of calculus too, in most cases, and it's the first one we forget because we don't use it all the time. But in differential equations and what follows, we will be using partial fractions several times, and so please do get out your Calculus 2 book and review the theory of partial fractions, because we will see it again. That's a promise. Now, let me decide, because we've got a few minutes left here, which of these problems I want to do next. I think we'll work the Maserati problem. So I need to clear this screen. And let's take a look at page 93. Problem 1. Now, I'll go over the problem with you because I know you probably don't have your book in front of you. No reason why you would. The problem says that the acceleration of a Maserati is proportional to the difference between 250 kilometers per hour and the velocity of the sports car. If this machine can accelerate from rest to 100 kilometers per hour in 10 seconds, how long will it take for the car to accelerate from rest to 200 kilometers per hour? So this is a problem about applying a force where you've got a resistance, and the resistance in this case is is the air pressure against the car. And if we were engineers designing a car, we know that that would depend upon the velocity of the car and also depend upon the shape of the car. So we don't build things that move fast like airplanes and rockets with square fronts, do we? We make them kind of pointy so they'll slice through the air. There's an engineering term called form factor that can be calculated from the geometry of the cross section that an object presents to the air. And for this problem, they've kind of lumped the form factor into the statement that dv dt is proportional to 250 minus the velocity. dv dt is proportional to 250 minus the velocity. Now, what is dv dt? This is a motion problem, so v is velocity, and the time rate of change of velocity is acceleration. So this is telling me that the acceleration for this car is proportional to 250 minus the velocity. And so you can see that what the model says is, as the velocity increases, then this number is going to become smaller and the acceleration is going to decrease. And so the acceleration decreases. And why would it decrease? Because the resistance from air pressure builds as the car goes faster and faster. So we can make this an equation if we'd say dv dt is equal to, let's add a constant of proportionality in here, 250 minus v. So now we've got a differential equation instead of a proportion. And I know that rest to 100 kilometers per hour in 10 seconds. So that's a given. We don't know maybe right now how we're going to use that, but that's a given in the problem. And then the question is, how long to 200, was it 200? Yeah, 200 kilometers per second. And we can calculate the acceleration here over the first 10 seconds because what is acceleration? It's time rate of change of velocity. So at least the average acceleration over the first 10 seconds would be the velocity at t equal 10 minus the velocity at t equals 0 divided by my delta t, which would be 10 kilometers per second squared. So that may come in handy. That may come in handy later. And also, we haven't written it out explicitly. We know that v of 0 is equal to 0. It's starting from rest. And v of 10 is equal to 100. So just piddling with the given information to be sure that I understand the given information and that I understand what is asked us to find. And this is what we're asked to find. So let's see if we have enough that we can kind of get started here. So I know that dv dt is equal to k 250 minus v. So there's my differential equation. I can write that in more familiar form as v prime is equal to negative kv plus 250 k. Now, if I would rewrite that as v prime plus kv equal 250 K, I would recognize that as a linear equation, first order. Of course, I could also factor a K out of here and say this is equal to K 250 minus V. I guess, that's what I had originally. But in this form, I see that we could say V prime. Let me divide through by 250 minus V. 1 over 250 minus V dV is equal to minus K dt. These are the same. It's the same equation. It's just different algebraic variations. And I recognize this as a variables separable first order. So which is it? Is it a linear equation? Find the integrating factor, multiply, recognize what's on the left as the derivative of something, and then finish that procedure? Or is it variable separable? Which is it? Caleb?
I guess you could do either one.
Perfect answer. It's both. And so we can use either technique, whichever technique we choose. Now, I did this earlier and I just used the variable separable. I think day in, day out, that's probably simplest. So using the variable separable, you could use either, but using the variable separable, I've got a natural log V minus 250 is equal to minus K T plus a constant, and that will boil down to V is equal to C e to the minus K T plus 250. Now, for problems of this type, we've seen them before. We've got one arbitrary constant, that's C, but we have a parameter K that we haven't determined yet. It was a constant of proportionality, and we haven't figured out what that is. And so to fully find a particular solution here, we need two conditions. But in this case, we know that V of 0 is equal to 0, and we know that V of 10 is equal to 100. And so that will let us find C. And in the interest of time, I'm going to find C is negative 250, and K is equal to 0.051. So I used this equation, this solution, general solution, and two conditions that I knew to evaluate C and K. And now I've got a particular solution that I'm being lazy, I don't want to have to write it out, but I think this is it. V is equal to negative 250 e to the negative 0.051 t plus 250. And what we want to know? We wanted to know when is V of t equal to 200 kilometers per hour. And so you set V equal to 200 and you solve this, and that would be 31.6 seconds. So 200 kilometers per hour, that's pretty fast, 31.6 seconds. I've got 5 minutes left. Rather than start another problem, I'll tell you a story. I spend a good deal of my summers in Canada, where I listen to the Canadian Broadcasting Company. That's like NPR. And after a holiday, the Ontario Provincial Police will broadcast the most ridiculous excuses that they received over the holiday for people driving crazy. And one day, Canada Day is July the 1st. It's equivalent to our 4th of July. Big 3-day weekend. They always make it a 3-day weekend. And they caught somebody on the main road from the little town that I stay in, south to Toronto, driving a little bit over 200 kilometers per hour. The speed limit's 100 kilometers per hour. And he was doing a little bit over 200. And so they stopped him, pulled him over, and they said, well, you know, what were you thinking about? Why were you driving this fast? And he said, man, I had to. He said, a car just passed me with 3 naked girls in it. So he thought that would be a sufficient excuse. Well, he got some radio time anyway. It's the most ridiculous excuse of the weekend for exceeding the speed limit by a factor of 2. Wow, that's, I mean, 200 kilometers per hour is what? 100 kilometers per hour is between 60 and 65. So it's 120 miles an hour. That's pretty damn fast. Probably faster than you should be driving. Okay, well, I just did that to fill the time. I've got another problem that I've worked out that I want you to look at. There's another lesson besides reviewing calculus 2. And the other lesson is there are differential equations that you know how to solve, but without practice, you'll have trouble setting them up. So setting up the differential equation is as much an art as solving the differential equation after it's set up. And you can do both, but you have to practice. Can't do it without practice. I posted some new problems for you, problems of the type that we worked today. And so you can get started on those. You've got a week to get them done. And I have an office hour later today and one on tomorrow. So kind of look up those times. Feel free to drop in or email me with questions. But meanwhile, have a good day.